All right, good morning. Welcome back. I hope you guys are all doing well, staying safe, and ready for the best class of the day. Hopefully you enjoyed your day off from chemistry yesterday, too. I'm looking for a few people. Looking for Kim, Joey G, Jumila, Tristan, Nidal, and Philip. If you're here, please let me know. Hey, there's Phil. Hello, Phil. Good morning. All right, let's see what's happened for the best class of the day. Quote of the week, simple one. Dream big. Say this all year. Dream big. Dream your dream. Whatever your dream is in life, hopefully after this year, hopefully after high school, after college, you go out there and dream your dream. Set your goals in life. You have one shot to live your life. You have one shot to go out there and make the most out of it. You might as well set the bar high and dream your dream. Maybe you want to be a chemistry teacher. Maybe you want to be a performer. Maybe you want to be an elementary teacher. Maybe you want to be an engineer, RN, a doctor, whatever it may be. Go out there and dream your dream. Dream big. All right, today's Tuesday, June 8th, 2021. To day 4. We are going to continue on with unit number 11, which is nuclear chemistry. We will finish up topic number 2, which is natural and artificial transmutation first. We'll analyze the exit pass questions. We'll do the odd questions together, and I'll give you some time to work on the even questions. Once we're done with that, probably like 20 minutes into class, we'll jump into topic number 3, which is fission versus fusion. We'll definitely go through fission today. Tomorrow we'll go through fusion. We'll go through the guided notes. We'll watch one flick on fission versus fusion, and then we'll save actually this next portion for next class. So really our daily agenda is to hit topics, or just to go through the agenda 1, 2, and 3 for today. Below are the attachments. You see the reference table. May need that today. Probably don't need it much. And then that video to right there, the crash course on nuclear chemistry. We will watch that one today too. Your final exam is Thursday, June 10th. You will have a final this Thursday, June 10th. What's going to be on the final? Fair game for the final. Anything on the final could be units number 1 through units number 11. They're all fair game for the final. The final exam is going to be 30 multiple choice questions. It's going to be on buzz. It's going to be graded. If you don't do the final exam, you're definitely not going to do well for the 4th quarter. Or if you don't do the final exam, you're not going to do well in this course. Treat this final exam as if it's the Regents exam. We don't have a Regents. So let's see, did you learn anything from me or this course? This virtual experience? Hopefully we'll never have this virtual world again, but it's good to have because in college, there's a lot of courses offered online and you'll be more experienced than people that didn't have virtual world technology. Did you learn anything from here? Hopefully you're ready for that final exam. I am not reviewing. We just reviewed for the post-test. It's on you. Final exam this Thursday. You'll have the full block to complete 30 multiple choice questions. Any questions on the routine for this week? Really, any questions on the final exam? Any questions at all? Final exam Thursday, 30 multiple choice questions. Any questions for me? Start preparing. We just prepare for the post-test. Preparation is the key to success. Yeah. High-five friends. All right, let's get right to it then. Let's figure out what we talked about last time. We talked about natural and artificial transmutation. Let's scan through it, see where we were last time. It's been a while since I've seen you guys. But here's the guided notes. We went through unit number 11. We already went through nuclear stability and equations. We went through artificial and natural transmutation. And later today, we'll go through fission versus fusion. Let's figure out where we're at. So topic number 1, checking it out now. Nuclear stability. Oof, that's a little smaller. Nuclear stability. I'm trying to figure out this paint function. I just realized how to use this paint format. But anyways, topic number 1, nuclear stability. We talked about radioactivity. We said unstable nucleus emits radioactive particles or energy. We said what makes something unstable, an unstable atom, unstable nucleus, is because the proton to neutron ratio is not 1-to-1. If it's a 1-to-1 ratio, it is stable. If it gets out of that ratio, then it's not going to be stable. It's unstable. We said atomic numbers greater than 82 tend to be unstable. So elements greater than lead, Pb, tend to be unstable. We talked about radioactive emissions, the breaking up of a nuclei that releases energy or particles. We said the things that can be released could be an alpha particle, a beta particle, a positron, or a gamma radiation. We looked at those in table O. We looked at what these all mean, what these subatomic particles or notations for nuclear chemistry represent. We figured out the charge of these particles. We looked at something like a cathode ray tube where they took a particle and they put that particle through a magnetic field. We noticed that there's a positive charge in this magnetic field, there's a negative charge. We know that opposites attract. So the line that veered up towards a positive had to be negative. That was a beta particle. We figured out the line that went right through with no change in pattern is neutral, gamma. And we figured out the one that deflected down towards the negative had to be a positive charge, which was an alpha particle or a positron. We looked at that. We looked at an example, a diagram to figure out the charges of these particles. We talked about radioactive decay giving off a lot of energy. We said a small mass effect, where a small amount of a mass is converted into a ton of energy. And that we'll explore today with fission and fusion. Mass effect is where a small amount of a mass is converted to a ton of energy. Take a little piece of something and make a big explosion. We talked about chemical reaction. You should know how to balance that chemical reaction. Last class, we talked about artificial and natural transmutation. We started off with natural transmutation. Natural transmutation is a spontaneous disintegration of a nucleus of a certain atom, causing a release of emission particles and or energy. What does that mean? Automatically breaking up of a nucleus and something is released. It's automatically decaying into something else. One element changes to another, something is released. The things that can be released can be an alpha particle, could be beta, could be positron. We looked at the properties of those. We looked at some examples of natural transmutation. One element changes to another element, something's released. A particle is released. Here we go. We have potassium changes to argon, and a positron is released. Natural transmutation. Second example, we said Pu changes to U, and a particle is released. Natural transmutation. One element changes to another element, and a particle is released. Last example, one element changes to another element, something is released. A beta particle is released. In those equations above, we predicted what the unknown variables were. We talked about artificial transmutation. Artificial transmutation, human-made or man-made reactions in which a nucleus is bombarded. So there's a nucleus here, and you're going to force something into it. A high-speed particle causes a nucleus to give off a proton, neutron, or some particle. Why are these important? Because man-made elements of the actinide series, come from the man-made elements. There's a very, very small, very, very quick, short half-life for a lot of these elements. What are these elements good for? They're good for medicine. A lot of these ones are good for medical applications. We'll talk about that for the last topic. How are particles accelerated? We talked about that with accelerators, but we also talked about artificial transmutation. Artificial transmutation, man-made reactions where the nucleus is bombarded. Think about that. Nucleus is bombarded. That is the reactant side of the equation. Let's look at the second example. Second example here, we have an atom of aluminum, and then you have an alpha particle, which is that fish. You're taking that, you're smashing it into the aluminum. Once those two things react, a new element is created and something is released. Hopefully you can see the difference between artificial and natural transmutation. This is artificial transmutation. Let's look at another artificial. ES. An element, ES, is bombarded with an alpha particle, the fish. Take that alpha particle and smash it into the nucleus of ES. What's going to happen? It's going to create a new element and something is released. That is definitely another example of artificial transmutation. So is the first example, artificial transmutation. One element plus another element. You're taking those two things together. You're combining those two things. What happens? It creates a new element. Something is released. Second to last example, similar to an artificial transmutation. You're taking a beta particle, you're smashing it with PM, and then a new element's formed. Should have been something released, or maybe it was a gamma particle. That would have been released there in that situation. That is artificial transmutation. The odd man out here, this one is natural transmutation. Hopefully you can see the difference there. Natural transmutation, why? Because one element, PO, automatically or spontaneously or naturally breaks down to another element and something is released. The alpha particle is released. That example would have been an example of our natural transmutation. We looked at artificial, we looked at natural transmutation last class. Please open up the guide or the exit pass for topic number 2, artificial and natural transmutation. We will do the odd questions. A couple of you guys already did it, so you guys can hang out for a while. We will do the odd questions. When I'm done with that, I'll give you some time to work on the evens. So again, exit pass, unit number 11, topic number 2, natural and artificial transmutation. Here we go. Let's go through this. I'm doing the odds. You're going to do the evens on your own. If you have enough time to do it right now. Question number 1. Let's get this equation on a separate piece of paper. Let's just focus in on that one equation. Question reads, in the equation, P32 yields S32 plus X. The particle represented by X is what? We want to know what X is. I don't care about anything else but that equation, and I want to figure out what the heck this X is. So we want to figure out what this missing link is going to be. So you want to fill that in. Here we go. In this situation, you would figure out the law of conservation of mass. You would use the law of conservation of mass. What does that mean? That means whatever the mass is on the reactant side has to be equal to the mass on the product side. So the masses on both sides must be equal. You'd also use the law of conservation of energy, the law of conservation of charge. The proton number on the left side has to equal the proton number on the right side. The reactant side must be equal to the product side. Here you go. My work here, I'm color coding this. You can see this. So P has a mass of 32. Hopefully remember the number on top is the atomic mass. Oh, Leo, you're tired back there. Keep me on. Mass is on the top, and on the bottom is going to be atomic number or proton number. So red is atomic mass. Atomic number is going to be the blue. So we have 32 I told you think of the yield sign as equals 32 plus x. Oh, that's easy. X plus 32 equals 32. What plus 32 equals 32? X must be equal to 0. So x is going to be equal to 0. So the mass of this unknown particle has to be equal to 0. Let's go through and analyze the proton number. Okay, we have 15 equals 16 plus x. Solve this equation. What does x equal? What plus 16 equals 15? Oh, -1. -1 plus 16 equals 15. True. So the numbers are going to be in standard notation, 0 over -1. All right. We want to figure out which particle it's going to be. So 0 over -1. Let's check out table O in the reference table. 0 over -1. Check out table O in the reference table here. Boom. Table O, there it is. Staring at me. 0 over -1 has to be an electron, or 0 over -1 has to be a beta particle. Number 1, X is going to be represented by X is going to be a beta particle or an electron. Electron, there it is. Beta particle or an electron would be the missing link. 1, the best answer is choice D. 1, the best answer is choice D. Let's try another one. Number 3, we're doing the odd questions together. You're going to do the even questions on your own. Question number 3, in the reaction, 14N plus 4HE yields 17O plus 1X. It wants to know what is represented by X. First things first, there is a typo here. That V should not be there. So don't worry about that V. We want to solve for this expression, just like we did the last time. So here we go. The proton numbers are on the bottom. The mass is on top. The reds are the masses. Think about this process again. Whatever's on the left side has to equal the right side. You have a mass of 14 for nitrogen, plus helium has a mass of 4, equals 17 plus 1. Guess I don't need to do all this. Sorry, solve for me, right? We don't need to do all that. Let's not even waste any more time going through that. We have X, which is 1 over 1. Let's look at the reference table instead of going through and try to solve anything. It's not going to prove anything. The math's already there for you. We need to figure out which one's X, 1 over 1. Look at the reference table. Table O, 1 over 1. Again, focusing on X. We have 1 over 1. 1 over 1, there it is. Or 1 over 1, there it is. It is a proton, or it's a hydrogen atom. Oh, there's proton. It's got to be the answer. It's got to be choice C. Neutron, you can see, is going to be 1 over 0. Triton would be an isotope, tritium, of H. And this one you'll see a little bit later. This is going to be an isotope for H as well, 2 over 1. 1 over 1 has to be the proton, or if it said hydrogen, that would have been the answer too. 3, the best answer is choice C. 3 is definitely C. Next one up, number 5. Here we go, let's solve this one. Give the reaction. Which particle is represented by X? I want you to figure out which particle is represented here. Please take a minute, solve this expression, solve for the unknown. Please put your answer in the chat once you're done. So number 5, please put your answer in the chat. I will sit here quietly and I'll work my way through it, and you can follow along with me if you're stuck. Please record your answer in the chat once you have the correct answer or an answer you feel good about. 0 over -1 represents what? Thanks, Nadina. Thanks, Tintin. Oop. Please record your answer in the chat once you have a response. 0 over -1. So you saw my work on how we got the value 0 over -1. Find 0 over -1. 0 over -1 represents, hey, a beta particle again. So I have 21 people online right now. I have 2 people that knew what they're doing. That was a beta particle. 5, the best answer is going to be beta. You saw our work there. 0 over -1 is beta. Next up, number 7. Try this one out. Given the nuclear reaction, TH234 yields PA234 plus X. What's X here? Solve for X. Please record your answer in the chat once you're ready. Thanks, guys. Please record your answer in the chat once you're ready. It's just my way to gauge whether or not you guys are understanding this. Zero over -1. That's the values we should have got for standard notation. 0 over -1 happens to be a beta particle. Again, is it always going to be a beta particle? No, it's just the way that these questions rolled out here. Beta particle is 0 over -1. Again, that's a beta particle. 7, the best answer is choice B. Does anybody at home have any questions? Seven, the best answer is B. A couple more to analyze. Number 9, give the reaction. This reaction is classified as what? Use your knowledge from last class. What do you think this reaction is? Please put your answer in the chat. This one's going to be Wendy's question. B? You know what you're doing. All right, cool. Several people at home said B, and so did somebody in class. I don't know who, but Wendy. She said B. This reaction is classified as artificial transmutation. Why is it artificial transmutation? Remember the examples we went through? We said an element, Al, transfers to a new element, something's released. So transmutation is always going to be when one element transfers to another element, something's released. This would represent natural transmutation without the HE there. If I have the HE there, you're taking the alpha particle and you're going to bombard the alpha particle with the aluminum. So you're going to take this alpha particle, the fish, you're going to smash it into the nucleus of aluminum. That's going to create a new mutation. It's an artificial transmutation. It's not beta decay because beta decay is 0 over -1. There's nothing there with 0 over -1. This would be an alpha particle. That's an alpha particle. Fission, fusion, we didn't talk about yet, but maybe later today we'll understand what those two reactions are as well. That's definitely artificial transmutation. Last question I'm going to do together, question number 11. Which equation represents nuclear disintegration results in a release of a beta particle? Oof. Show that to your friends not taking chemistry class. They'll be like, what are you talking about? Which equation represents nuclear disintegration resulting in a release of a beta particle? What do you think the answer is for number 11? Please put your answer in the chat. Santino, you're up. What's the best answer here? A. I'm going to go with that one right here. Nuclear disintegration, nuclear breakup with a release of a beta particle. What's a beta particle again? Do you remember the numbers or no? 0 over -1 is a beta particle. Check out table O. 0 over -1, there's beta. So a beta particle has to be represented in this equation. All right, so it looks like D. How come it's not C then? So the first thing he found is the beta particle, but there's a beta particle there. I asked him, why isn't it choice C? There's a beta particle there, there's a beta particle there. And he's going to tell me because you said release. Choice C is not releasing, it's bombarding. Choice D is releasing a beta particle. A beta particle is given off, it's emitted, released. If it's on the reactant side, it's going to be smashed with the other element of the reactant or bombarded. If it's on the product side, it's going to be given off or released. Best answer is going to be choice D. Thank you, Santino. Thank you for everybody at home. That's the best answer for number 11, choice D. All right, I'm going to give you 5 minutes to finish up the rest of these. I know I gave you extra time. Some of you guys are already in good hands. You already figured out how to do this. So I'm going to give you 5 additional minutes to finish up the even questions. Once we're done with this, we'll switch gears and move on forward. So 5 extra minutes to complete this right now. Putting you in breakout rooms. Please join your breakout room. Please complete it. If you do not finish this up for some reason, this will be due on Saturday. Give you till 12:18 to complete this. Please join the breakout room. Please complete this. Not many questions. So you have till 12:18 to do this. Please join the breakout room. Please complete the exit pass for topic number 2, natural and artificial transmutation. Please join the breakout room regardless if you already did it. Thank you. All right, welcome back. Hopefully you finished it up. If you did not finish the exit pass, that is going to be due by Saturday. It's graded. You should get at least a 50 on it. We did half of them together. Please do the rest of them for homework. If you did not do it, please turn it in by Saturday. All right, next up on the plate is topic number 3. We're going through fission versus fusion. We have guided notes, unit number 11, nuclear chemistry. Please open that up. We're on topic number 3 now. So topic number 3, we're starting off a little different than we have in the past. What we're going to do, I'm going to ask that you define what fission is right from the start. Use your cell phone, your Chromebook, the textbook, the online textbook, whatever you want to use. Define fission. And when you're done with that, I want you to find a picture or draw a picture that you can relate to. I probably would get one from the internet. And pull it in to what the fission reaction looks like. You'll have 5 minutes to do so. So again, you're going to define fission. Once you define fission, find an image that you can relate to, that you can think of for fission, and paste it within this text box. I'll give you 5 minutes to do this too. So please define it. You have now till 12:25 to do that. Once you have your definition, please put it in the chat. So please define it. Put it in this text box. Find an image. Put your definition in the chat to me so I could see your responses. Define fission. Need one more definition, please, for fission. Please put in the chat. All right, cool. Thank you very much for doing that. Appreciate it. It's 12:25. A few people responded with definitions for fission reaction. Is yours similar to this? Is it the same? Whatever it may be. Let's check it out. So Nadina said, when an atom splits into two different parts and it releases energy. Oh, an atom splits into two different parts and energy is released. Asim said the action of dividing or splitting something into two or more parts. Oh, starting to see a common term here. Dividing or splitting of something. So that's definitely a common term. Splits. Breaking up, splits. So those two are on the same wavelength with that. They talked about splitting or dividing. Jimmy Law said when an atom splits, splits again into two parts, either through natural decay or when it is instigated with a lab. It releases energy. Oh, see another common bond for at least the two ladies here. Common bond is releasing energy. Releases energy. Those definitions are great. Alex said, dividing something into two or more smaller parts. Cool. You're splitting. Every one of those situations, you're splitting the atom to smaller things. You're taking something big and breaking it into smaller components. With that reaction, it gives off a ton of energy. So those definitions are a good place to start. A fission reaction, I would just open up a new tab and type in the toolbar, fission reaction. Go to the images and find an image that you can relate to. Doesn't mean anything to you. So a lot of these images are like breaking up of something. Find one that you like that you can make sense of. I'll take this one right here. I don't care which one you pick. I'll take this one. Why not? I'll take this one. I'm going to copy the image. I'm going to paste it within that text box, that cell to the right. All right, that's fission. Looks like fission, but I'm going to give you some more notes just to make it complete. We have a neutron. This neutron, what's going to happen here in this reaction? A neutron is going to be bombarded. You're going to take that neutron. You're going to smash it into this uranium-235, this big thing here, this big atom, big nucleus. You're taking that, you're smashing it into the nucleus. When that process happens, it's going to create the splitting of the uranium into two smaller components. So you're taking this neutron, you're throwing it at this, take a baseball or something. Pretend for a second. Take a baseball or something. You take that baseball, you throw it at an atom hard enough, it's going to break that atom into two smaller pieces. With that, a lot of energy is created. Only thing missing here, I think, would be energy. I would like to have energy in the diagram, but it's not. No big deal. All right, so let's go through. Let's finish some notes here for fission reaction. So complete it. Let's get through fission. A fission reaction, I'm going to cap lock, I'm going to bold, I'm going to highlight. You know my routine by now. A fission reaction is the splitting of a nucleus, splitting of a large nucleus, into two or more fragments, a process that produces additional neutrons. Yes, I definitely am going to grade this guy in notes. This last unit, we will collect it. Process that makes additional neutrons and a lot of energy. Energy is going to be given up. That's huge. Energy is released in the situation. What causes a fission reaction? It's initiated by the capture of the neutron. So that neutron right there, it has to be captured. It has to be smashed into the uranium for this reaction to occur. It's initiated by the capture of a neutron that is fired or bombarded at the nucleus of an atom. Capture of the neutron that is fired or bombarded to the nucleus, not at, to the nucleus of an atom. Right? Right. So the capture of a neutron that is fired or bombarded into the nucleus of a larger atom, or uranium typically is going to be the one you're using here. When this happens, as that neutron's fired into it, it creates a lighter element, lighter atom, lighter element is formed. And is more stable. Is more stable than the parent element. Yeah, I had to reword this a little bit. Once you take that neutron, you fire it into a uranium, it's going to create a lighter element, and it's going to be more stable. So that 1-to-1 ratio, that proton to neutron ratio, it wasn't stable initially. So it could have easily broken up the, not easily, it could have broken up the uranium for a more stable, lighter element. Fission reaction. What could you expect to see for a fission reaction? In a fission reaction, you could see uranium-235. I'm going to hit control, period, 235, control, comma, 92, control, comma again, uranium, plus a neutron, which is going to be control, period, 1/0. Uranium plus a neutron yields, you have those two components, it's going to yield the forward reaction. It's going to give you Kr92 over 36 krypton plus Ba141. I know it's going to take some time, guys. 56 MPa. What else is going to be given off? It's also going to give off some neutrons. So 3 neutrons. 3 neutrons would be released. That's a coefficient. 1/0 neutron. What else is released? One more thing. This is the big one. I'm going to drop the bomb. One more thing's released is going to be a ton of energy. Energy. A lot of energy is created here. Like the nuclear bomb, energy created. It's definitely an exothermic reaction. Why is it exo? Because energy's on the right side. This is a fission reaction. A fission reaction I think of as the atomic bomb, nuclear bomb, the thing that ended World War II. Yeah, you should be aware of the history of the end of World War II. You should be aware of that. So that is a chemical equation for a fission reaction. Uranium plus a neutron yields a smaller element plus another smaller element, krypton plus barium, plus 3 neutrons are released, and a lot of energy is created. A fission reaction is a chain reaction. A fission reaction is a chain reaction. A chain reaction is a chemical reaction, a reaction in which a change in a single molecule or element, a change in a single element or molecule, changes until, I'm sorry, change in a single molecule. Oh, I made a mistake here, not changes. Single element or molecule makes many, okay, there you go, molecules or elements until a stable compound is formed. Until stable element or molecule or compound is formed. So it's going to go through this chemical reaction until you have stability. So these chain reactions are going to keep reacting until it finds that stable 1-to-1 ratio. Trying to find that balance. You guys want that balance in your lives. You don't have that balance, things get all crazy. You don't want this hot and humid weather like we had this morning. It's crazy. Get bad hair days for the females or some males that have like the longer hair. This is like a frizzy day. Look at me. Frizzy day today. It happens. I know, guys. You want to find that equilibrium. Chain reaction, a reaction which a change in a single element or molecule makes many molecules or elements until a stable element or molecule is formed. Okay. Tongue twister, a lot going on there. A chain reaction. There's a picture to the right. You have one element which is going to break up to smaller ones, which is breaking up to smaller ones, to breaking up to smaller ones. It's continuing to happen until you have stability. It's stable. Kind of looks like cell division here. Cell divides, makes new ones, makes new ones, makes new ones. They get bigger, all the way throughout. The importance of a chain reaction, a fission chain reaction. Why are they important? There's some uncontrolled and controlled chain reactions. The importance of a chain reaction and uncontrolled chain reaction. Uncontrolled fission chain reaction results to a nuclear explosion or the atomic bomb. Or the atomic bomb. So a chain reaction out of control could result to atomic bomb or a nuclear explosion, and or a controlled fission chain reaction so if you have a controlled fission reaction, it's huge for society. Why? Because it's used for producing or making electricity, nuclear energy, used as a source of energy. Nuclear reactions, source of energy. Nuclear energy, it's huge. It gives off a lot of energy. The mass effect, a small mass creates a ton of energy. These aren't as popular in the United States as they are in Europe or Asia, but a lot of countries are really liking them and developing their nuclear energy because it creates so much energy. So energy is something you're always going to be exploring. You're always going to be hearing about hot topics for science. Is solar power the way to go? Is wind power? Is hydroelectric power? Is nuclear power the way to go? We're always trying to figure out the best, most efficient type of energy where there's not much waste or fallout. We want safety to be an issue. Every 4 years when you hear the presidential debates, they're going to talk about energy. What you're playing with energy. Maybe nuclear energy is on the radar. Maybe not. All right, guys, that's going to be it for the notes for today's class. We'll end class for today. We'll analyze a video on crash course video on fission versus fusion. That's going to be it. After this video, that's going to be it. So again, you should definitely know fission reaction deals with the splitting of a nucleus. You should know fission reaction is going to be dealing with uranium. And you're taking that mass and creating a ton of energy. We'll analyze fusion next time. But before we do so, I do want to wrap up with a video, crash course video on fission versus fusion. Enjoy.
As I said before, chemistry is, like many aspects of your own life, all about a search for stability. Last week we talked about radioactive decay in order to become more stable. But what is this elusive stability that all things seem to be striving for exactly? In nuclear chemistry, it simply has to do with keeping the nucleus together. If the nucleus is going to break apart, then that's not going to be something that lasts very long. Stability really is kind of just a way of saying it can exist. And the amount of energy that holds each proton or neutron in an atom's nucleus is the same amount that's released when it's removed. This is known as binding energy, and it's one of the fundamental principles of nuclear chemistry. It's actually what we mean when we talk about nuclear energy. Now, I'm not gonna lie to you, nuclear chemistry is terribly complicated, but we have a way of understanding it that, while not exactly simple, is one that I'm sure you've heard of. The binding energy of an atom is calculated with a formula: E equals mc squared. Probably the most famous equation in the world, and since it was first hit upon by a young patent clerk in 1905, it has become synonymous with scientific genius. Part of why it's so famous, I like to think, is because the logic behind it is so elegantly simple and yet totally counterintuitive. But it's probably also famous because it's important. It explains one of the most powerful sources of energy known to humanity. E equals mc squared is formally known as the mass energy equivalence formula, and it states that mass is interchangeable with energy. Okay, there's a lot there in what I just said. To tease it apart, consider the nucleus of an atom of oxygen: 8 protons and 8 neutrons. Collectively, by the way, these particles are known as nucleons. If you were to add up all the individual masses of all 16 nucleons separately, and then compare that to the total mass of an actual oxygen nucleus, you'd find that there's a difference between the two. Specifically, the mass of the nucleus, exactly 15.99 atomic mass units, is lower than the mass of its individual nucleons put together, in this case 16.13 AMUs. That mass went somewhere. That missing mass in the nucleus, known as its mass defect, is actually present in the form of energy. It's the energy that holds the nucleons together. So, for example, the mass defect for an oxygen atom is negative 2.269 times 10 to the negative 28th kilograms. To find out how much binding energy that missing mass amounts to, you can use it as the m in Einstein's formula. This ingenious little equation relates mass and energy by a simple proportionality constant, and thanks to Einstein, we know that constant is the square of the speed of light, or c squared. Solve for E, and you find that the binding energy in that oxygen nucleus is 2.04 times 10 to the negative 11th joules, with the negative sign indicating that the energy is being released. Now, of course, 2.04 times 10 to the negative 11th is a very small number. That might surprise you, but hold the phone. That is just for one single nucleus. If we multiply that by Avogadro's number to find the energy change for a whole mole of oxygen nuclei, a mere 16 grams of oxygen, we get an amazing 1.23 times 10 to the 13th joules of energy. To produce that energy with coal, you would have to burn 420,000 kilograms, 420 metric tons of coal. That energy is what we mean when we talk about nuclear energy, the binding energy that's released when a nucleon is removed from its nucleus. Now, to dislodge one of those nucleons and unleash that energy, there are two general types of nuclear reactions: fission and fusion. Fission occurs when a large nucleus splits into two lighter ones. Fusion is the opposite, when two light nuclei join together to form a heavier one. In both cases, the products of the reaction are more stable than the starting materials, and this is, as always, what drives the reaction. This is a graph of the binding energies of various elements compared to their mass numbers. Elements with very high binding energies, such as iron 56, are very stable and rarely undergo nuclear reactions, but elements with lower binding energies can react much more readily. If the nucleus is heavier than iron 56, iron-56, it will tend to break into 2 or more smaller nuclei, a fission reaction. If it's lighter than iron-56, it will more likely participate in a fusion reaction, joining 2 nuclei together to form a heavier one. But the most important thing to notice here is that with both fission and fusion, stability increases as a result of the reaction. Fission is the type of reaction that we use more often because it's the one that we're better at initiating and controlling, at least so far, and whether it's used in power plants or bombs, the most common fuel for fission is uranium-235. There are several ways that it can react, but the reaction is almost always triggered by hitting uranium with neutrons from another source. When that happens, the uranium splits into smaller atoms. One such reaction produces krypton-92. Yes, krypton is a real thing, along with barium-141. 3 free neutrons and lots of energy. This energy is released mainly as the kinetic energy of the escaping particles, which is immediately transferred to the surroundings as heat. Some energy is also released in the form of electromagnetic radiation, such as visible light, X-rays, and gamma radiation. Nuclear power plants use the energy released by these reactions to convert water to steam, which then is passed through turbines, spinning a generator, powering cities and stuff. Because of the enormous amounts of energy these reactions can release, nuclear power plants can potentially produce lots of electricity. But there's also, I think you may have heard, some serious drawbacks. For one thing, as you know, atoms rarely exist in isolation. We write the equation of a fission reaction as if it's just one atom, but in reality, that one atom is surrounded by many, many more. And if one little neutron can trigger the reaction, and that reaction liberates 3 more neutrons, well, I think you could see where this is going. If the reaction isn't controlled, each reaction triggers 3 more, and every reaction releases the same amount of energy, which adds up fast. This is pretty much the definition of a chain reaction, and it is the basis of the remarkable power of a nuclear weapon. The same type of reaction occurs in nuclear power plants, but those reactions are controlled in several ways to keep them from getting out of hand. The fact is, these chain reactions have the potential to produce far more heat than the plant can use, so much more that the temperature can easily rise to dangerous levels, enough to melt the uranium. This is the meltdown that you hear about, and most reactor cores are immersed in water to disperse the heat and prevent this from happening. But that's not enough on its own to control this thing. If the chain reaction is allowed to run freely, no amount of water can remove the heat fast enough to prevent a meltdown. The real way we control nuclear reactions is with control rods. They're made of materials that readily absorb neutrons, and they're inserted between the fuel rods of uranium to slow the neutrons down and therefore slow down the reaction. They can be put in more to slow the reaction more and lift it out more if you need more heat. Now, the other sticky wicket of fission reactions is the stuff that's left behind. These reactions not only produce products that are still radioactive, they produce tons of them. Lots of different troublesome kinds. Like we saw last week, uranium undergoes many different types of nuclear decay, so not only does each uranium atom produce isotopes of krypton and bromine, but that process also produces many other isotopes of other elements. And as these various nuclei break down, they release more neutrons and more unstable products, and the process continues for a long time. All of these reactions eventually yield stable products, but they have half-lives ranging from a few years to tens of millions of years. The products with shorter half-lives stabilize pretty quickly, but they release particles and energy like crazy during that time, so they're extra dangerous. The ones with longer half-lives decay more slowly, release less energy, but that means it takes a very, very long time for them to stabilize. So long, in fact, that for human purposes it may as well be forever. That means they'll always be an issue in our environment, which is why we're always looking for ways to store them and keep them out of our way. Fusion reactions, as you'd expect, are very different from fission. For one thing, the energy released in many fusion reactions dwarfs even the huge amount released by fission. You might be familiar, for example, with the wonderful work done by our sun. The reactions that power the sun are like most fusion reactions in that they involve very small nuclei, like isotopes of hydrogen and helium. This reaction begins when 2 atoms of hydrogen, accelerated by the sun's fantastically high temperatures and contained by its high pressures, join to form an atom of deuterium, an isotope of hydrogen. This fusion of particles releases a positron and some heat energy in the process. Then another atom of hydrogen is joined to the deuterium to form helium-3. This step also releases a lot of energy in the form of gamma radiation. When 2 atoms of helium-3 are available, they join together to form an atom of helium-4, as well as 2 atoms of regular hydrogen, which then can be used to begin the process all over again. This final step also, as you might imagine, releases a large amount of energy in the form of mostly gamma radiation. So this is a chain reaction too, but it's not a self-perpetuating one like we saw before. This reaction requires a total input of 6 atoms of hydrogen, but it only produces 2 in the end, the remaining mass being released in the form of helium. For this reason, more fuel is always needed, which is why our sun is gonna run out of hydrogen in about 5.5 billion years. We can produce fusion reactions here on Earth too, but they're not very useful for us because we haven't figured out how to control them. They're super useful if you just want to blow up a big city, though. Just to be clear. depending on your definition of use. One reason is, as you can see in the mass energy graph, light nuclei that fuse together undergo a much larger energy change than heavy nuclei that break apart. That means their reactions release far more energy than fission reactions do, so much more that it's nearly impossible to contain and therefore use. Also, because fusion involves joining nuclei, the reaction has to overcome the really strong repulsion that naturally exists between their positive charges. For this reason, fusion reactions can only occur when particles collide at very high speeds or under very high pressures. At these mind-blowing speeds, the kinetic energy of the particles produces insane temperatures, like in the 100 million Kelvin range, at which point the material being accelerated actually exists in the form of plasma. So not only are those speeds really hard to reach, but material at that temperature, how do you control that? Which is why we can't use fusion for things like generating electricity, which would be super nice. We've only found applications for it when we don't need to control it at all, like in nuclear weapons. So as you can tell, there is plenty of room for new ideas in nuclear chemistry. Fusion would be really great because it would produce a lot of energy and you'd just get helium out of the process, and helium is awesome. How can we use radioactive materials more efficiently? Is there a way to achieve the speeds and manage temperatures that come with fusion? And how can we do this stuff without blowing our faces off? You've already taken the first step by learning the basics. It's up to you how far you want to go from here. Maybe you'll write the next totally crazy, ingenious, and counterintuitive equation that takes us to the next level. For now, though, thank you for watching this episode of Crash Course Chemistry. If you paid attention, you learned how Einstein's famous formula helps us calculate the binding energy of a nucleus from its mass defect. You also learned the difference between fission and fusion. You saw an example of each one, and you learned about their applications in the real world. This episode
All right, guys, that's it for today's class. I'm letting you out quite a bit early today, so enjoy the rest of the 10 minutes off. If you didn't finish up the XPass, please do the XPass right now. Next time, we'll obviously go through fusion, and you will have a final exam on Thursday. All right, guys, take care. Have a good day. Stay cool. Stay safe. Bye.